We'll start now. Hi everyone. Good afternoon to you. Can you hear me well? Okay. So thanks a lot, first of all, for coming over here for my talk. My name is Ankur Tyagi, and I'm here to present a tool that I've been working on. It's called Angad, and it's basically about analyzing malware using visualization. So we'll try to understand how what all techniques are available right now to visualize arbitrary binary data, and how one of those techniques can be useful for classification and clustering of malware samples or unknown files that we get on a daily basis, and to classify them into known good or known bads. To quickly introduce myself, I work as a senior malware research engineer at Qualys, and on the net you can find me using my handle 7s3ram. Alright, so here is an outline of the talk. We'll first of all try to understand what solutions do we have right now to analyze malware, and the issues that we have with those solutions. So there are lots of techniques to analyze malware, but everything has its own drawback. So we'll try to get some understanding of what exactly malware analysis is and what are the challenges. We'll look at a clustering technique. Alright, so malware analysis, if you have worked or looked at malware samples, you would realize that analyzing a piece of file or unknown binary, it's not straightforward. There are lots of issues, but on a very primary level, there are two challenges. And the first challenge is that most of the samples these days is obfuscated. There is a lot of effort taken by the authors of the malware to keep it stealth, to keep it undetectable. But these challenges can be countered. We have multiple solutions, but the fact remains that it is very difficult for us to analyze each and every sample on its own, and to do that in an automated manner. We have sandboxes, but not all the samples will execute fine in a sandbox. There are certain samples that not show behavior within a sandbox because they use anti-virtualization or anti-sandbox identification methods. Then again, the second problem is that the volume of samples that are coming in, it's really high, right? So even if we have a really good malware analyst sitting and analyzing malware 24 hours a day, we will not be able to we will not be able to complete all the samples that we have found for that day, all the new unknowns that we have found for the day. The problem is that the malware, as we are moving ahead in time, the malware is evolving in complexity. And the second problem is that the volume of these samples is really high. So it's not possible for someone to sit down and manually analyze samples, right? So there have been lots of interesting proposals over last many years, and these solutions try to address this problem in multiple different ways. Some people try to employ techniques which are very specific to debugging or disassembling a sample and then understanding its internals, and using that understanding, converting that understanding of the sample's behavior or the packing techniques into a model, and these models can then be used to classify unknowns that they get in future. So these are some of the generic manners in which the community is trying to address this problem. There are different solutions that are also applied to malware analysis. For example, some people are trying to use bioengineering algorithms or genetic algorithms to the problem of analyzing malware. So they are parsing the malware binary, which are typically malware in this context. For this presentation, we'll focus on Windows executables P32 and P64 files. So people are trying to parse those samples and extract data that they are interested in, and then convert that into a form that can be consumed by algorithms that are already known to work well for classification and clustering. So these are some of the techniques that people have proposed. They have worked well, but the challenge is that it will work well for a certain set of samples, and it has to be constantly evolved. It has to be worked upon, And this is a problem that will always remain. We will not be able to create a solution that can work for everything, that can automatically analyze and classify an unknown all the time. Most of the vendors, if you must have seen, so most of the vendors, they have their own proprietary solutions. They have their own engines to to analyze a malware. These solutions are not public, and unless you have a license or if you pay them a fee, you will not be allowed to use it. Some people have a cloud service. You can subscribe to that, register and submit your unknown samples to them. They get your samples and you get to know whether the sample is good or not, or whether it might do some harm to your system or your infrastructure. So some people are actually interested into analyzing samples and coming up with new ways. They spend their time and they come up with new projects per se. So these could be open source, but these are mostly hobbyist projects that people use to analyze malware samples. But the interesting takeaway here is that with the progress in time, we are actually seeing that the detection mechanisms are getting more accurate. We are getting new ways or new techniques of identifying malware samples, and they are much better than the techniques that we had in the past. But also the fact remains that malware authors are aware of this thing, and they are constantly working on making it more difficult for us to identify their samples. So in my daily job, I get a pile of samples to analyze, and I have to use sandboxes. I can use, for example, we have a VT virus roller subscription feed, but it's not enough for us to have VT tell us that this sample is good or not, or if it is a known bad, if a AV identifies it as certain family. We would like to know what exactly this malware does. We have to spend some time, and doing that for hundreds and thousands of samples that we get on a daily basis, it's not feasible for one person to do it. So the challenge here is that we have certain solutions that are very specific, and we don't have a generic solution for this problem. A generic solution might help because we can reduce some overhead, and at the same time we can use that solution to make sure that we are safe in future. So if we have a generic detection signature for a malware or for a malware family, that same signature will work for newer variants of the same malware. So let's say in future you have a malware ABC and you have a new variant for that. All the new variants, because they are derived from the same source tree, they will have certain features that are common across all the variants. So that if we are able to create a generic detection mechanism based on that, on the core family, core behavior of the family, we will be able to use that signature across all the variants of the same family. And if we can categorize certain samples together based on their type, for example, remote access trojans or ransomware, if we can create a generic detection mechanism for ransomware as a category, all the ransomware samples that we can have in future can be detected via that generic signature. We will have a high number of false positives as well, because generalized solutions tend to have really high TP, but interesting thing is if you only look at TP, you're missing out a lot, because generalized solutions have a really high false positive rate as well. So we will still need specialized detection mechanisms, because we would need to attribute what exactly or where this threat came from, who was the author, what campaign it was part of. So these are some of the things that can only be done if we have generalized detection mechanisms. In this talk, I will be focusing on visualization. So people have worked on applying visualization techniques towards malware analysis, and there have been a lot of talks, a lot of papers, even projects. There are services online that you can use to submit your samples and get a visualized view of this of the input file. That view can help you classify and understand what the sample does. It highlights the prominent features of the sample. the list is seemingly never ending. There has been a lot of research already done in this area. And one of the techniques that I would like to focus on in this talk is using Hilbert curves for the visualization. So Aldo Cortese, he has posted, he has talked a lot about using Hilbert curves. Hilbert curves are a type of space filling curve, and he has talked a lot about how to use these to classify and cluster samples, and specifically how to use these to classify malware. You should check out his blog. The links are here in the presentation. He also has a project called binwiz.io. Some of you might have used it. So this project helps you to submit a file. It's a web portal. You can go and submit any input file that you would like to visualize, and this file can then be, it will be rendered as a Hilbert curve. All the sections of the file will map to certain offset within the curve, which will be a 2D representation of the input stream, and you can interactively look at the content of the file in a different manner, in a visualized manner. Daniel Plowman, he has also written a lot about using Hilbert curves, and the interest, that is the research that was really interesting for me was the work that he did in aggregating import APIs into something he calls API vector. And API vectors are a collection of import APIs, and it's a compact representation of an import table for the PE file. And these API vectors, he then proposed a way of visualizing these import vectors as Hilbert curves. And these import vectors look like QR codes, and that is why he refers to them as API QR. We'll have a look at these. So first of all, let's spend little time on understanding what exactly a Hilbert curve is, and to see and to understand why we should be using Hilbert curves. Hilbert curves, the image here on the left, it's a map of the internet. It's taken from XKCD195. All the addresses within the IPv4 address space, 2 raised to 32, 4 billion addresses, everything has been compressed into this image. Hilbert curve, they have a very special property. Everything, all the elements within the input set that are similar will be grouped together. So as you can see, we have groups of multicast addresses for various registries grouped together. This is a hand-drawn map, and the one on the right is a algorithmic generation of the same content, but this is much more accurate than the one on the left. This again shows the same data, but in a different manner. These blocks have different meaning. Each block and the color code represent certain block of IP header space, and combined, this image shows all the addresses within the IP space. The most important thing that I would like to highlight in this slide is that Hilbert curves are really, Hilbert curves have really excellent spatial indexing feature and locality preservation. So spatial indexing, what does this mean? You can think of a hash map. You have some input stream, and you map it to a offset within a 2D space. That is spatial indexing. Clustering is also one of the important characteristics of Hilbert curve. So these features are really important when we have a challenge like clustering of unknown data or classifying unknown samples into known good or known bad. Again, the same thing. So if we use Hilbert curves and feed it some malware sample or an unknown binary as input, it will map it into a 2D diagram or onto a 2D space, and all the bytes from the input stream will be mapped to a unique index or unique offset within the 2D space. So this can be thought of as a visual hash. Like how you have a cryptographic hash, you can think of this image as a visual hash. So every time you have a input stream, it will always generate a same or a similar visual hash, similar Hilbert curve. Here is an example. So all these images are generated from 3 different files. These are unknowns as of now. So we don't know what the samples are. They are known bad, but let's consider that these are unknowns for us. And these are 3 different files. But looking at the Hilbert curve representation, we can say that structurally these files are very much similar, which means that these files might come from the same source, or they might have same binary layout, or they might have same content within them as well. Because the cryptographic hashes are different, it means that the files are different. They might have some changes, they might have a different packer, or they might have a different layout, but content wise they are still the same. They have exactly the same number of bytes and the same offset for those bytes within the file. Hilbert curves also have a drawback. This is important to consider because Hilbert curves are good for spatial indexing, but only for the data that retains its offset. If you have some data, so this was actually animation from Aldo Cortesi's blog, because this is a PDF presentation, you will not be able to see it move around, but this black blob of data, this image animation was created using some input file which has some data, and the data is being moved around. So for each frame, the data was moved at 1 byte offset, and the Hilbert curve representation was created, and all those Hilbert curves were combined to create this GIF. But the idea is that this blob will keep moving. It will not be constant. The shape will keep changing, and the blob will keep moving around in the within the 2D space. What this means is that it is very difficult for us to represent the same data if it is at different offset within the input stream, because the Hilbert representation will not be unique, and as such visual hash using Hilbert curve is very sensitive to the offset of the content that we are trying to visualize. Alright, so to tackle this problem, Daniel Plowman, like I said, he proposed a solution to use import API. So the images that we saw earlier, these images are the exact representation of the input files. We take those input blobs and represent them as a Hilbert curve. This can be done for any file. But because we already know that these are malware samples, these are P32, P64 files, we can parse them, and we can extract data that we think is of that would be interesting for us. For example, in his proposal, Daniel Plowman, he proposed that he suggested that let's use the import addresses, the import address table, parse it, extract the Windows APIs, and map them onto a bit vector. So the image that you see here on the right, this is a API QR representation. It's a 1024 size bit vector. It has 1024 Windows APIs mapped into it. All APIs have a fixed location, so no matter what file you have, all APIs, the common APIs will always be at the fixed offset, and as such, the problem that we saw earlier of the data moving around will not be there. So we will be, because we are making sure that all the bytes are at a fixed index. This image helps us create a much more, or this image can be used for classifying and clustering of samples, because all samples will have same APIs at the same index. We will have a look at the example, and here it is. The image at the top, this is a API QR created for a sample, and these APIs, the different colors represent different types of the APIs. So certain APIs would be for the certain APIs are of networking, certain APIs might be for crypto. So from the import address table, we extract APIs. These APIs actually tell us what behavior or what to expect when the sample will execute, what kind of behavior we might see when it is actually executing on the system. And these APIs are mapped onto a bit vector. And this is how the API QR will look like. And the image at the bottom was actually animation. So this the below image was created using a sliding window. So for the sliding window, what we are doing was for all the APIs that are executing within a certain time window, we were grouping them together, creating a Hilbert curve for them, and then combining all these images together. So this gave you an animated representation of how the malware is evolving. So over a sliding window, it showed some behavior and then moved on to a different window and showed a different behavior. If its behavior is constantly changing, you will see there is a change in the number of APIs that are being used or the type of APIs that are being used. This is a similar representation but of different data. This data is now coming from the behavior report. So earlier we were looking at the APIs that were extracted from the import address table, but this time what we are doing is we are looking at the representation from the behavior report for the sample. So we execute it within a sandbox, capture all the API calls it is making, and map them onto the bit vector. Same technique, different data. As you can see, there is a lot less activity here. The malware imported a lot of system DLLs, and there were a lot of system APIs as such that were mapped onto the Hilbert, the API QR. But when it actually executed, there were a lot less number of system calls. Maybe it identified the sandbox, or maybe it was it actually didn't have much activity to do, and because of which we don't have much to see here. But this is again a representation of the malware's activity behavior. So once we have these images, the image that we saw at the start, then the image we saw for the import table, and the image for the behavior table. So these are three representations using Hilbert curve of different data. First one, use the actual file as input, all the bytes from the file fed as input to the Hilbert curve representation. And second one, we use the import address table. For this image, we use the behavior APIs. All of them are represented using a similar algorithm, Hilbert curve. And when we look at them in group for multiple samples, here is what we see. On the left, so these are representations for different files. Hashes are on the left side. All these files are different. But if you look at the first column of images, which is the representation of their structure, all of these files have a similar structure. If you look at the second column, this is the representation of their import APIs. All these files have similar import APIs, and as such a similar Hilbert curve representation. If you look at the behavior, so the third column is for the behavior APIs. Again, it is similar across all these samples. So these images actually tell me that it now becomes very easy for me to conclude that these samples belong to a same cluster. They might be the same malware family, or they might derive from the same malware family. They could be different families but coming from the same source. This gives me a quick overview of what exactly the sample is, and how can I group it to a known bad or a known good entity that I have already indexed in the DB. So if I already know that row 1 is a known bad, all other samples, all other files that have similar images or representations also are known bad for me. So we can use AV detections for this to classify whether something is known good or known, or we can manually analyze one of the samples, not all the samples in the cluster. So this is one cluster, we have 4, we can have hundreds and thousands. We can analyze just one sample, we don't have to analyze all of them. And even if just one of them turns out to be a known bad, everything else is known bad or a known good for that matter. Alright, so I'd like to quickly show you a demo. So it's a easy to use tool. It's in Python. It uses the libraries that are already available, Scurv and API Scout, and then creates a wrapper on top of it, indexes everything into a database, and uses image similarity to identify whether those images are similar or not, or what images are similar, and to use that similarity percentage to index or to group samples into clusters and index all of that data into a SQL backend. So you there are two ways of running it. You can pass it the input directory which has So we need behavior data or the report that we get from a sandbox. It can come from VirusTotal, it can come from any other sandbox. We also need the malware sample itself, because for the first column we need to have the actual binary, actual malware. So everything can be kept into a folder and you pass the path, and now it starts creating visualization. So the first column, we call it byte view. The second column, IAT view, input address table, and the third table is the behavior view. Once we do this, we look up into the SQL backend that we have. Whatever samples we have already indexed, we'll compare it against those, and this is what we get. So it, based on the imports, this sample, the input sample, is similar to certain sample, certain hash 01BF6 43 A4, and here is the match percentage. So the images that we have created based on the import APIs for the input sample is similar to these files that we have already indexed in the DB, and the match percentage is 100%. Now this is a very precise match. If there is 100% overlap in these images, the imports are exactly same. This, however, does not mean that the samples will behave exactly similar, because imports are just an indication of what the malware might do when it executes, but they are not a definitive way of classifying samples. So we move forward, we look at the behavior, and under the behavior we see that the sample is similar to a lot of other hashes that we have already indexed in the DB. The match percentage is well above 90 for all of them. If you look at these, so right now these samples are, let me take you here. So the samples that I have indexed in the DB, okay, so samples that I have indexed in the DB, they actually don't have, we are not showing the family, or we don't already know what these samples are. We just know that the input file belongs to a certain file, or it is similar to certain files, and the match accuracy is 100%. But what exactly are these files that it has matched upon? So the input is unknown, and let's say we already know what the match samples are, the samples that we have already indexed in the DB. So this hash actually belongs to a malware family called Mookil, and we see that the input sample also matches on the basis of import table, it matches to the same sample from the same family with a match accuracy of 100%. So let me, so the spoiler here is that the input sample is also from Mookil family. So we didn't fed this information into a tool, and we just ask it to create images and then compare. But the matches that we have found are only for the Mookil family. All the matches based on imports and behavior is for the Mookil family itself. There is a visual representation also. So here it is. These are all the hashes that we have indexed in the DB. These were unknowns when we actually indexed them. Then we looked up on VirusTotal and figured out what these samples are, what families they belong to, and we named this cluster as Mookil. So, but interestingly, as you can see, if it is not clear, so there are certain IDs that are printed out for each match. These are cluster IDs. So for the imports, we have a cluster 09B0, and for behavior, we have a cluster 070373. So these are the clusters that the sample has matched to. So the sample, interestingly, belongs to two clusters and not just one. So if it was part of a malware family, it should have, if the accuracy was high, it should have belonged to just one cluster. But that is not the case here. What we are seeing here is that the malware sample belongs to two clusters for now. It could belong to multiple clusters. And why is that? So let's have a look at the visualization. Here are all the samples that have that are part of the Mookil family, and all of them have been laid out on the same image, on the same page. As you can see, the first column, you can see that there are two distinct groups here. The first three hashes have different images. All of these images are more or less same, but the the next two groups, they are not similar. So Mookil, actually the data or the samples that we have indexed in the database, we have two variants of Mookil here, and that is why we see two clusters, and the tool is able to indirectly identify that there are two clusters. So it is not similar to just one type of file, it is similar to two types of files that we have. It can belong to cluster A or cluster 2, but everything is coming from the same source. Why? Because although the byte view representation, the first column, is different for all the files, it's not common for everything, there are certain groups, and the import representation is also divided into two groups. If you look at the behavior reports or the behavior visualization, all the reports, all the hashes have exactly the same behavior, right? So although their structure is different, their imports are different, all of them actually behave in a very similar manner. And that is why we identified that all of these samples belong to the same cluster. They are part of the same malware family, although they might have used a different packer or they might have used a different obfuscation technique, because of which their imports were different, because of which the behavior should also have been different slightly, but because if you have a different packer, you need a different, if you pack two files using different packers, their unpacking mechanisms will also be different, and that will be reflected within the behavior calls. But it will be a small percentage of the overall activity that the malware is doing. So the overall percentage of the overlap that you see between two API visualizations should be very high if the sample belongs to the same family, which is the case here. All behavior reports, the third column, are exactly same. This report interestingly has no behavior, so I am using the VirusTotal as the source of truth here. That is the sandbox that I'm using to capture behavior data. VirusTotal has no behavior captured for this sample, so that's why the representation is empty, but you can use some other sandbox as well. Again, all the images that are created for the all the Hilbert curve representations that are created for the behavior API are common across the samples that we have clustered here. Now this tells us, this has helped us in two ways. This has helped us to first of all group all the samples together as one cluster and then further segregate them into different versions. So this is Mookil, these samples belong to the Mookil family, and at the same time there are two variants, at least the variants that we know of as of now and we have indexed in the database. These variants behave similar, but they are packed in a different manner, and as such we have, we can actually also say that the author might have modified, or the author might have changed, the code might have been reused, it might have been shared over the dark web, and someone else would have got access to source code and would have packed in different manner, but they would have repackaged the same thing. They have not made any changes to the code itself. The behavior still remains the same, but just the packing mechanism, it has changed. To give you another example, DOV is a malware family. It's a Trojan. As you can see here, the byte view representations are really good, but it is like the problem that we have seen with Hilbert curves is that they are very sensitive to the offset of data or the number of bytes that are common. If the offset changes within the stream, or if the number of bytes it changes, it is very sensitive, and the resulting representation will not be similar for two files, which is what we are seeing here. So not all the files in the first column are similar. Again, the same case with import address table. We see hardly any imports in the file, but if you look at the behavior calls, there is a lot of overlap. All these samples, using VirusTotal as a source of truth for now, we have found out that these belong to the malware family DOV, and if we cluster them using Ankur, we can also see that all of them belong to the same cluster. So we were able to cluster on the basis of behavior. We can cluster on the basis of the structure of the file, or only based on the imports. And we can use this as a model. So if you have overlap for all these three, the accuracy will be higher. But if you have overlap for just, let's say, behavior and not for structure, it tells you that the malware sample has been packed in a different manner. It behaves same, but it looks different. Or if you have different, let's say, the same technique can be used in a different manner. So as you can see, all the first three or four of these samples are packed via UPX. UPX is again a very common packer. There are different versions of it. So we can use the first column, the byte view representation, to identify what kind of packer is used. So all the files that are packed by UPX would look more or less the same. So this can again, but they will not behave exactly similar. So when you have overlap over byte views, we know that the structure of the files are same. They might come from the same source, or they might have been packed in a different or a similar manner. Sorry. So because they are packed in a similar manner, they have a similar packing technique that is used. If you know what packing techniques one file is using, you can apply that same logic for other files. You don't have to spend time analyzing and figuring out what exactly this packer is. Again, the same thing. So we have two clusters. We had two clusters over there. These are samples from APT33. All these samples, obviously, we don't know the packer. The packer might be custom. There might not be a packer. As of now, from the data that we have here, we don't know what the packer is. But we can see that clearly there are two distinct groups. Except for the last hash, everything else looks exactly similar and behaves in a similar manner. The last hash is really interesting. This looks different from the other samples. It has slightly different import address structure, but the behavior, it's totally empty. So this is a APT sample, and it's very easy for these samples to identify sandbox like Cuckoo that VirusTotal is using, and it's easy for these highly sophisticated threats to evade sandboxes, and that might be the reason we don't have behavior for this particular sample over here. But the rest of the samples that we have here, because we were not able to cluster the last sample into APT group because we don't have enough data for the structure or the behavior. But based on the VirusTotal report, we already know that this is APT, and that is why I have included it here. This is to show that if we don't have enough data, we might not be able to complete the picture. We will not be able to tell what exactly this is, but we can give some hints. So this, because the imports are common, it belongs to APT33 or family XYZ. It might belong to different families at the same time, because we don't have enough data to validate the fact that this is only part of APT33 and not something else. All right. So yeah, so that's it for the demo. The tool is open source. It's already hosted on my GitHub. You can use it. You can, if there are any bugs, or if you find that something is not working, please let me know. It's a work in progress project. I'm already adding some new features. I'm trying to add features to automatically classify and tag samples. Trying to think of ways this can be used by people without actually running it from the command line, if it can be hosted as a web service. So things are moving, and I'm trying to add new features, fix bugs as I can. So if you find something is not working, probably I'm working on it already, or if I'm not, please let me know. This is my handle, 7s3RAM. You can reach out to me on Twitter, on Google, and thanks a lot. Thanks a lot for your time. Sure. Yeah. Yeah. Exactly. Yeah. So I have found such patches. There is a certain rate of false positives that is not acceptable, but I have found that it is only common for certain malware samples. So samples from the APT category, they don't have such overlap. Only malware families that are commonly used, or malware families that try to, for example, the category ransomware or rats, these have certain overlaps. It is not common across all the types of malware. It is only common for certain types of malware. So for certain categories, there is a percentage of false positives. For example, if I remember correctly, for ransomware, the false positive rate was very high. It was around 5%. So this is not acceptable, because 5% might still sound low, because 5% is still a number that I'm not happy with. But I found that this is only for the ransomware category. For rat, the number was somewhere around 6 or 7. But again, rats, they have a lot of network activity. And this is common for a lot of other files. And based on the network activity, the behavior APIs look similar to, for example, PuTTY or a different tool that has a lot of network activity. So there are definitely certain overlaps, but only for certain categories of malware samples. Sure. I don't know exactly if these if any AVs are actually using visualization per se, but yeah, definitely AV vendors, they have their own behavior analysis engines, and that is what I said. So vendors typically almost always have a proprietary solution because of business reasons, and they are not going to talk about it. But being in the industry, you get to know that, get to hear from people that yeah, definitely they have a behavioral heuristics engine. What techniques exactly are being used, it is not commonly known, so we don't know of it as of now. But because visualization has been talked about for a long time, it's been talked about at least for 15-20 years now, and there have been different proposals around using visualization techniques for malware analysis, but there is no authoritative tool. There is no tool like Wireshark that is that the tool for visualization of binary samples. There are lots of really good tools, but there is not just one tool. So we don't know if AV vendors are copying that tool or they are doing something on their own, but they already know the research is already there. So who knows, they might already be using it. Thanks. Any other questions? All right, guys. Thanks a lot. I will be around. If you have any questions, just feel free to catch me somewhere. If you cannot find me, you can reach out to me on Twitter, on Google. 7h3RAM, that's my handle. Thanks a lot for your time.